This is going to be a quick review of the Coulombic attraction packet that you guys completed last week. Remember that Coulombic attraction is going to be the basis for pretty much everything in this next unit on periodicity. So in Model 1, we have three different scenarios where we've got a proton and an electron, and they are different distances apart. You can see that as that distance goes up, the force of attraction, which is measured in newtons, the SI unit of force, is becoming smaller and smaller. As two charged particles get farther apart, their attraction decreases. So the positively charged particle is a proton, the negative one is an electron. I would expect a force of attraction there because opposite charges attract. The independent variable in this would be the distance. The dependent variable is the force. As we are moving the electron further away, we are seeing that that causes the force of attraction to go down. Complete sentence. As the distance between particles increases, our force of attraction decreases. If the distance between a proton and an electron is 0.5 nanometers, which would be longer than any of these, I would expect the force of attraction to be less than it would be if they are 0.3 nanometers apart. If two protons are 0.1 nanometers away from an electron, what would you expect the force of attraction to be? Greater or less than 2.3 times 10 to the negative 8th newtons. So when I have one proton and one electron at 0.1 nanometers, my force is 2.3 times 10 to the negative 8th. If I were to add another positive proton, I should slide up so we can see this. If I were to add another positive proton, it would make sense that my force of attraction would be greater because there would be a greater positive charge. In Model 2, we've got three different atoms here, lithium, sodium, and potassium, which on the periodic table are all in group 1, lithium, sodium, potassium. And we've got Bohr models drawn here, where each circle represents a principal energy level. So lithium only has 2 principal energy levels, sodium has 3, and potassium has 4. Also indicated by the period that they are in on the periodic table. The arrows here represent our force of attraction. As the arrows get thicker, we are seeing a greater force of attraction. We already looked at those elements. They're in the same column. Circle the outermost electrons in each model. I didn't do that. So we got one there, one there, one there. All elements in group 1 have one valence electron. As we are moving from the smallest atom down to the largest, the distance between nucleus and valence electrons is going up. As you're adding shells of electrons, the outermost electrons are getting farther from the nucleus. As we move from the smallest to the largest, what is happening to our force of attraction? It's going down. The arrows are getting less and less thick as we move down. Is this consistent with the information in Model 1? Yes, it is. Just like in Model 1, where we had our protons and electrons at different distances, as the distance goes up, like it did in Model 1, the force of attraction goes down. As the distance goes up in an atom, my force of attraction goes down. Model 3. This time we want to look at the effect of the force of attraction based on the number of protons. Notice the distance is all the same here because we only can change one variable at a time. If we were to be changing distance and number of protons, we would have no idea which had the effect. So independent variable here, my number of protons represented by those. My dependent variable, still force of attraction, still measured in newtons. A complete sentence that describes this relationship. As the number of protons is going up, the force of attraction between proton and electron is also going up. What would be the attractive force on a single electron if 5 protons were in the nucleus of an atom? Show mathematical work. So we see that with one proton, my force of attraction is 2.3 times 10 to the negative 8th newtons. If we double the number of protons, we double the force of attraction. When we triple the number of protons, we triple the force of attraction, meaning it's a linear relationship. Every additional proton is going to increase the force of attraction by 2.3 times 10 to the negative 8th newtons. So if I take 5 and I multiply by that number, I get 1.15 times 10 to the negative 7th. So notice that even though that first number looks smaller, negative 7, 10 to the negative 7th is bigger than 10 to the negative 8th. If a second electron were placed to the left of a nucleus containing 2 protons, like in set D, so basically if I put another electron over here, and that was also 0.1 nanometers, predict the force of attraction on both the original electron and the second electron. Explain your prediction with a complete sentence. So I would predict it to be exactly the same. Each electron is individually attracted to the nucleus. It does not matter how many electrons there are. Each one has its own pull on the nucleus, or the nucleus has its own pull on the electron, I should say. Compare it to gravity. The force of gravity on your body is from the Earth. It doesn't matter how many people are on the Earth. We're not divvying up Earth's gravity. Each one of us feels force of gravity due to the Earth, independent of the other people on the planet. If you were the only person on planet Earth, you would have the exact same force of attraction due to gravity. So as we're adding electrons, each electron is going to have a pull from the nucleus. We do not divvy that up. It's very important. All right. And we go on to prove that here. If you read that when you were doing it, it goes on to explain exactly what I just said. So each one of these, and I'm assuming that this is also 0.1 nanometers, is going to have an equal force of attraction. All right, model 4. Now we're looking at elements sodium, aluminum, and chlorine on the periodic table. Sodium, aluminum, chlorine. So they are all in the same row on the periodic table. I circled the outermost electrons. Sodium's in group 1, it has 1 valence electron. Aluminum in group 13 has 3. Chlorine is a halogen in group 17, it would have 7 valence electrons. Which has the strongest force of attraction? It's chlorine. Look how thick that arrow is. The thicker the arrow, the greater the force of attraction. As you move from the smallest atom to the largest atom, does the distance change significantly? It does not. Because sodium, aluminum, and chlorine are all in the same period, they all have the same number of principal energy levels. They're all in the third period, so they all have 3 principal energy levels, meaning that distance from valence electron to nucleus is pretty much the same in each one. So if the distance is the same, this change in force of attraction cannot be due to the distance. If I write in my protons, I've got 11 protons here, 13 protons here, and 17 protons here from their atomic number. Can the attractive force be explained by a change in the number of protons? Absolutely. We already saw in model 3 that as we increase the number of protons, we are increasing the force of attraction. So in these atoms, as the number of protons goes up, it makes sense that the force of attraction is going up. For each element below, circle the element whose atoms will have the stronger attractive force. So for this, I'm going to need a periodic table. Barium and calcium, here and here. They're in the same column, which means the distance is going to be the driving force in determining what is more attractive. We know that as we go down a group, distance is going up, force of attraction is going down. So as we go down this group, the distance is going up, force of attraction is going down, which means barium is going to have a less force of attraction than calcium. So calcium will have a greater attractive force. For chromium and copper, in the same period on the table, which means the distance is not going to change significantly, just like in this model. But copper has 29 protons in its nucleus, whereas chromium only has 24. More protons, greater force of attraction. Copper is going to be greater than chromium. And for argon and xenon, again, we're back to two elements in the same column. So we're dealing with distance. As we go down the group, distance increases, so force of attraction decreases, which means argon, which is higher up, would have a greater force of attraction than xenon. And finally, consider the atom diagrams in Model 2, which was that model right there. When comparing elements in the same column of the periodic table, write in the number of protons. So when I write in my number of protons, 3 in lithium, 11 in sodium, and 19 in potassium. When comparing elements in the same column, which factor, distance to the nucleus or number of protons in the nucleus, seem to be the dominant factor? Distance is dominant. As we're going down, our force of attraction is getting less and less. Now we have two things changing here. We have number of protons, which should make it go up. And we have distance. As distance increases, my force of attraction should go down. Because it is going down due to the distance and not increasing, even though there are more protons, distance must be a more dominant force. Mathematical relationship. Whenever you're asked for a mathematical relationship, we're looking for directly proportional, inversely proportional, or maybe something like, is it a linear relationship? Is it an exponential relationship? I can say certainly that the relationship between distance and attractive force is inversely proportional. As distance increases, force of attraction decreases. And mathematical relationship between number of protons in the nucleus, Z. This confused a few people. Z is the letter that is always used to represent atomic number, which is the same thing as number of protons, so it's just a variable. And the attractive force, F. They are directly proportional. As my number of protons in a nucleus goes up, the force of attraction goes up. Directly proportional relationship.